Okay, let's start today's lecture. Today we are going to learn sorting algorithms in data structure. So we know sort is a very important function in computer science. And usually if the data is sorted, we can use like binary search, all those like fast algorithm to analyze them. To make it simple, in this chapter, we assume the data to be sorted are just integers. It's easier to show as an example, but for strings or other character, it's just the same. And also, it's the data is sorted like saved in an array, and it's sorted in ascending order. So the first question. Oh, this is on the someone did that. A sorting algorithm easy to develop. It's when I still remember when the instructor asked me this question when I was an undergraduate student. No one. The instructor asked like, what can you do if you are going to develop a sorting algorithm? No one. Everyone has some ideas, but no one says anything because we feel like it's an algorithm. It should be difficult. But the thing is actually, intuitively, if we want to sort an array, we can just check all the elements and find out the minimum one and put it someplace, right? And when you just search the remaining numbers and find out the smallest one and put it after the first one, and so on and so forth. This is like what we do in our daily life, right? So congratulations, that's just a sorting algorithm called selection sort. Basically, just select the smallest one each time and put it into the beginning of the array. So another algorithm it's also very simple, similar to selection sort, but it's called an insertion sort. It's like repeatedly inserting a new element into a sorted sublist. What does that mean? So let's see an example. So it's also just find out the smallest one, not find the smallest one, but just from the beginning and check. Assuming we start from the first one, 23, because there's only one element, we don't need any kind of insertion. But when we come to the second one, we can just assume the previous one, the 23 is already sorted, and we just need to put one into the correct position from this 23. Because one is smaller than 23, we just put one before 23. And now the sorted sublist contains 1 and 23. And we go to the next 10. We just put 10 to this sorted sublist, which should be between 1 and 23. And now all these three numbers are sorted. We just need to check the fourth one. 5 is smaller than 10. We just put before 10 after 1. This kind of every time we just put a number into its correct sorted location. And that's why it's called insertion sort. It's like we insert a new number into this previous sorted sublist. Yeah. These two algorithms are very intuitive and very simple to implement. We just need to swap numbers in this array. Another very popular and also simple algorithm is called bubble sort. I don't know if you have already heard about this news, but let's see. Oh, it's on from Mike.
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president, right? And you're going through the rigors now. It's also hard to get a job at Google. Right? We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer. Okay. What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1 million 32-bit integers?
What is the most efficient way to sort 1 million integers?
Bubble sort.
Bubble sort? Seriously? let's see how Obama says.
Maybe-
No. I think
That's not a.
I think the bubble sort would be the wrong way to go.
Bubble sort would be the wrong way to go.
Who told him? Okay.
I mean, even Obama, he knows about bubble sort. Yeah, bubble sort is it's very simple, and also it's better actually than the previous two algorithms. But for the million numbers, it's too many of them. We will discuss later why this kind of algorithm cannot be.
This number is external sort.
Yeah, you know that. Yeah, because for this bubble sort or insertion sort, if we want to use it, we have to put everything in the memory. A million members need a huge amount of memories, and this kind of calculation will be very slow. So bubble sort is definitely not a choice for this kind of thing. But let's see what is bubble sort. So bubble sort is like we just check the array from the first to the end, and each time swap the neighboring elements if they are not in the order. So let's see an example. So for example, we check from the first two to all the way to 1, and this time, because 2 is smaller than 9, we don't do anything because it's already in the order. But 5 is smaller than 9. We just exchange these two neighboring numbers. Now this time 5 is swapped before 9. And that's it. We don't, after the swap, we don't care about it. We just move to the next one. 4 is smaller than 9. We just swap 4 and 9. 8 is smaller than 9. We just swap 8 and 9. And of course, 1 is smaller than 9, we just swap it. We don't, like, you can see after the swap, it's possible that 4 is smaller than 5, but they are not in the correct order. But we don't care about it. We just do we just traverse all the numbers and do the swap for the neighboring numbers. And after that, we can check it again. This time, 4 is smaller than 5, we swap it. 5 is smaller than 5, 8, this is correct, but 1 is smaller than 8, we swap it again. And that's it. And we can check again, and this time 1 is smaller than 5, we to do the swap again. And after that, because as long as we do some swap operation during this process, we just double check from the beginning. And this time we swap again. And but this time, because everything is already aligned, we check everything is correct and nothing need to be swapped. That's done. The algorithm finished. That's bubble sort. It's like every element just like a bubbles swap from.
Bubble sort swap neighboring elements to get the elements swapped in ascending order. For example, when you one pass could be a step minus 1. For example, when you do one pass, you have 4 steps to sort the largest element to the end and to move the smallest element to the right,
Yeah.
the left.
Mm-hmm.
And then the second pass is the step 2. So it's 5 minus 2. It's the second pass is p minus 2. So 3. And then the third pass is p minus 3 is 2. And then fourth pass is p minus 4. 5 minus 4 is 1. And then fifth pass, we don't need to do that many steps. We just have to move. You only have to move from 2 and 1 to 1 and 2.
Yeah. So yeah, that's bubble sort. Another these are basically the most simple algorithms. I won't show the scripts today, but I will leave the implementation for bubble sort in the assignment, the next assignment. So for the next one, merge sort, they actually use a technique that we discussed last time called divide and conquer. Basically, just divide the list into 2 parts and sort the first part, sort the second part, and merge them together. Let's see this example. So we have a list. We just split it into 2 equal size smaller lists. And again, split again and split again, all the way until there's only 1 element. And this is a simple steps. But now next time we need to merge everything together. So in during this merge, we need to make sure that everything is aligned in the same order. For example, this one just 2 and 9, but this one we have to swap 4 and 5, and also swap 1 and 8, and swap again all the way. Just merge all these lists and finally get the sorted list. I will show the code later, like how this kind of merge steps can be performed.
I just want to inform you that the merge sort requires a bubble sort in the conquer. So when you merge the extra elements into 2-element array, you still have to do the bubble sort to rearrange the array. And then when you merge 2-element arrays.
No, not necessarily. When you merge 2 numbers, so let's see. There are many ways to achieve that. So of course you can use sort, but let's see, I have 2 array. The first one, 1, 2, 3. The second one, 4, 2, 4, 2, 4, 8. When I merge this list, I can actually use a stupid way. I can create another array, another list, temporary, and just save all these 2s in order in this way. For I can begin from the first one. 1 is smaller than 2. I place 1 here. Second one, 2 is equal to 2. I put it here. And 3 is larger than 2. I can put 2 here. And 3 is smaller than 4. I can put 3 here. And 4, because right now all the elements in the first one is already saved into this temporary array. I know the remaining one. I should just consider all the elements in the second list, which is already in sorted way. So I can just put everything into this temporary array. This is a way to merge 2 sorted array, just using another array to make things easier. Of course, it requires additional memory location, but it's easy to implement.
So you only need temporary array. You don't need to do bubble sort.
No, I don't need to do. I just need to compare, just merge 2 things together.
You just need to compare.
Yeah, you know what? Let's just see the script to make it easier. So this is the code for merge sort. You can see the function is easier. It's just divide the list into 2. Merge, in a recursion way. Merge first half, merge second half, and merge all of them together. But this actually merge function is a key. Like we use 3 index. The first index for the first list, second index for the second list, and also a temporary list will save the final results. So if the element in the first list is smaller than the second list, we just put it into the temporary array. Otherwise, we put the list 2 number in the temporary one. And we just do this loop. This loop only stops if one of the list is already, every number is saved into the temporary array. After that, we just need to check which one is empty. If this index is smaller than the length, which means there are still numbers in this list, we just put it into the temporary array. Otherwise, this one should be not empty. We just put all the remaining numbers into the temporary array. Yeah, that's a way to merge 2 sorted array. So next, let's talk about this quicksort. Quicksort is, as you can see from its name, it's quick. It's a very popular and a very powerful algorithm. When I was an undergraduate student, we have a team for this coding computation, and I remember the team lead. No matter what algorithm, like what question asked, like sorting something, he always said using quicksort, qsort. I think it's Java offered this quicksort function, qsort. Always said qsort. I don't know what is qsort at that time, but later I know that as it's qsort could be slow if the array is in certain shape, but overall, in most situation, it's a very good algorithm. So idea is similar to that divide and conquer, but this time we use a number called pivot. Usually it's just the first number in the array. Using that to divide the whole list into two parts. So the first part numbers are smaller than pivot, and second part is larger than pivot. So we're just using this way to basically just traverse the whole array and put everything smaller than pivot to the beginning. And once this kind of divide is finished, the actual algorithm is just sort on the first part and sort on the second part, like using this quick sort. It's also like recursive way, like divide and conquer is like divided into sub problems, right? It's just a recursive, like divide, sort first, sort second. Let's see a short description, a short like a diagram showing how this kind of partition is achieved. Actually, this is the partition is a key for the quick sort. This is not a good example. Let's change it. Okay, this one should be good. So we at the beginning we the first number as the pivot and start low. I mean, this one start from the second number. This one start from the last number. We just check all these numbers to this one. If it's smaller than it, we don't need to care about it. Otherwise, I mean, let's see the example. 11 is smaller than that. We don't need. Oh shit! Sorry, I just click reset, but I knew this is another example. But like 35 is smaller than 66. We don't need to do anything. Move to next. Still small. Move next. Still small. But this time 99 is larger than 66. So the way the algorithm will know this one might need to be swapped. So it just instead of it just move it. It just replace it with the last element. And this time we go from the next, still smaller, large. And, 59 is still smaller than 68. And 95 is larger than that. We first move the highest index left because this one is the one just moved earlier. So we don't need to move that. And this one is smaller. We will just do the swap. And next time, smaller, large, going from the larger end. Larger doesn't need to do anything. Smaller, swap. And the smaller, do nothing. And all the way until the two index reach the same location. But this is not the end because we still need to move the pivot into this, like this way. Yeah, we just move the pivot into this into the middle point because we know that the point here we already compared it is smaller than the middle point, so we can replace this number with the first number and make sure the pivot is in the right location. So that's the key, the main steps in quicksort. Just doing this kind of a swap. They do this kind of swap. I mean, the algorithm do it like this way because this is the best way to save both time and memory. You can see there's no additional array created. Of course, we can create a new array and just put every number, compare it, and save into a new array, but we will require additional memory location. You mean next? After that, it's already finished. You can see click next, nothing, yeah, because once we swap the pivot, that's done. That's yeah. So yeah, actually, let me show you how it is done in using quicksort. You can see it's like a recursive way. Just quicksort function and quicksort the left and the first from the first to the pivot, and from the pivot to the last. It's like a quick sort the first part and quick sort the last part, just using a recursion way. That's how recursion did, right? Recursion is it's hard to develop, but once you have an idea, the actual code will look very simple. And the partition algorithm is like this. The first one is a pivot, and the low start from the second, and the high start from the last one. And just to do the comparison, if it's smaller than the pivot, continue to the next. And from the high end, if it's, if the number is larger than the pivot, minus high, and move to the next one on the left. And the swap is as long as one of the while loop stops, which means there are some numbers that doesn't match this condition, which means they should be moved. Their location corresponding to the pivot should be moved. So we do the swap, and that's it. All the way, everything is finished. We just move the high index to the left one position again, and do this swap the pivot with that one, and finally just return the first index. That's about quicksort. This is a very, I will share the script to Moodle. It's a very smart implementation. So so next, let's talk about this heap sort. Heap sort, actually, there's many information here. I mean, the actual heap sort, the sort is not that difficult, but the case part is how to create this thing called heap. A heap is specific here, it's called binary heap, but many terminology, right? What does that mean? A heap is a binary tree, the following properties. So let me explain. What is a binary tree? So we call in computer science, we call this kind of structure a tree. Like it's just a linked list. Like a cell is connected to many other cells. It's called binary tree because every number, it can only be connected to at most 2 numbers. That's why it's called binary. And what is a complete binary tree? It's like when we save this thing in the memory, we save it basically like this one, we call this 2 numbers children, and this one is parent. We basically just save this one, and everything with its parent. Sorry, every parent with its children. And if it's just in this very good shape, I mean, no additional cells, this is a complete tree. And also similar, this one is also a complete one. I mean, although it doesn't have the right child, but everything before that is all the nodes, they have their children. So this kind of thing, this kind of tree is called a complete tree. But this is not a complete tree. Although this one, these 39 have 2 children, but 32 should be before 39. And they only have the left children. So this is not a complete tree. Of course, this one, 42, doesn't have the right children. So yeah, this is why the complete tree is just either in this very complete shape, or it's just one left children missing at the very end. And a heap is just every number in the heap, the parent is larger than its children. Like 42 is larger than 32 and 39. And also 32 is larger than 22 and 29. So as long as we create this heap and save everything into this in this ordered way, I mean, the sort itself is very simple. Like we know this one is always the largest one, right? It's larger than, it's greater than the following numbers. So we can remove this one. This is the largest one, and reconstruct this heap and remove the next one, remove next one. This way we'll just, every time we make sure that we remove the largest number in this heap. So the key, you can see is how to create this heap, and how after removing it, how we can regenerate it, make sure it's still in this specific structure. So this is complete binary tree. Yeah, and also heap is saved. I mean, binary tree is saved in every list in this specific order, like 62 and its two children, and 42 is two children, 32, 39, 48, 59 is two children, 42, 40. It's like in this specific order, like children, sorry, parent, children, parent, children. So we can, I mean, although like 44 is children of 59, I mean, there are two cells separate them, but we can just using the formula, like based on the index to compute what its children is and what its parent is. That's also why it's called complete. That's also why complete is very important. I mean, if this one is complete, there's only one cell missing here. Which, I mean, if there's a number there, they should be put all the way at the end, right? But if it's not complete, something might be missing in the middle of this area. We cannot using this formula to get its children and parent. So to create this heap, it's actually very complicated. I mean, the idea is not complicated, but the coding part is very complicated. The idea is you just like using graph, it's very easy. Add a number and add another number. If it's larger than 3, assign it as its parent. And 1 is smaller than 5, just assign that's children. Again, another number is larger than all 3 numbers. Sorry, it's larger than 5, we just put 19 into 5 as parent. And similarly, 11 is smaller than 19, we move to its 19th children. I mean, the idea is seems very simple, but actually, when you create it, it's very complicated encoding part. For example, you need to recreate the location like 22. When 22 is moving there, you have to replace 19 with 22 and put 19 into 22's children, and you also need to decide which side should it to put. Yeah. So and the remove is also similar to the creation. Just every time you remove, for example, 62 is removed. Now we first get the smallest number, the last one from the array to replace this location to the previous largest number, and then swap all these things. 9 is smaller than 59, just swap 2 of them. And smaller than 44, swap again to 44, and smaller than 17. And actually no, just compare. Usually always we compare the first left children first and then right children. So 9 is smaller than 30, just swap again. That's how this heap is reconstructed. Luckily, Java offers this heap class for us, so it's there. We can just use it directly, and I will also share the heap. I mean the code for heap to the Moodle for you to review later. It's a very long and complicated heap. I mean script to achieve this. So for all these algorithms we just discussed, this is the running time for them. So you can see bubble sort, insertion sort. Like we discussed previously, although this big O could be the same, but we know like some algorithm will perform better in most circumstances, and also actually no algorithm can perform better than n log n. That's if we just do this kind of comparison and swap. Any question about these algorithms?
No algorithms could be performing better. So we already found out that quick sort and heap sort is not designed to sort elements in ascending or descending order.
Not to design. What do you mean not design?
The quick sort and heap sort is not designed to sort elements to ascending order.
Why?
Because the reason why, because when you do quick sort, all the elements numbers would be different locations. would still be in some different locations, and you're only sorting them in groups. And heap sort is a bubble sort. So each heap sort is a binary tree.
Yeah.
So the elements follow the root, and then children, and then grandchildren, and then great-grandchildren.
Mm-hmm. But you can still get ascending order sort. I mean for heap sort also, although it's kind of descending order, like the one on the top is the largest one, but you can just use ON, like using one for loop to reverse everything, and that's ascending order. So there's another way, like this is kind of a tricky algorithm called bucket sort. That's a very I mean, this you can see, unlike others, it can be done in n plus t log O, I mean big O time, but that's because this algorithm, it doesn't use any kind of comparison. If, for example, similar this example, we have these numbers, like instead of using like a comparison, I can just create like a large list. Yeah, I can just create a large array, and the number one, I just put the index one, like for example, this array is called A1. I just using A11 to save the list. I don't do the comparison. I just keep, I mean, using the index to represent the actual value. And 2 is just the 2. 3 is 3. This way, as long as I save everything into this array, and also 2 again, put it here, and 4 is 4. And we only have 8, so we will put 8 into the 8th index. And all these things, they just remain empty, or remain remain empty. This is a very tricky way. Like if we only want to sort small numbers, and of course, because we might assuming I have like a million, there's a number called a million, which means I might waste a bunch of memory location because nothing should be saved there. But it's if we just want to sort about a group of small integers, this is a good way. Just using memory to make everything quickly. So finally, there's we just discussed that all these algorithms need to save everything in the memory to do the calculation. But if, let's say, we have 100 million numbers we want to do the sort, the idea is instead of put everything into the memory, we can just using a temporary file. I mean, divided the original array into some small segments and sort one segment, move one segment into memory and sort them one by one. Just everything, just sort them, and just using that merge sort idea to merge two results, merge again, and finally just merge everything together, and we will get a sorted list. Yeah, that's all about our today's lecture. Any questions?
Next week, Monday, will be online quiz.
Yeah, next Monday. Next Monday, yes. The thing is, actually, I might have a family issue. I will email us guys later. Because if I'm not available next Wednesday, I will have to teach on Monday, and then we can move the quiz to Wednesday. Yeah, but I will email everyone if that happens. So this algorithm, I mean, sort is a very tricky algorithm. You will definitely be asked during interviews